Hi everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 2 of my course, the SQL Server on VMware Accelerator. We just wrapped up a good introductory overview of enterprise virtualization. This module is going to focus extensively on enterprise storage underneath your SQL Server workloads. We're going to start by reviewing the types of storage that are currently available, the actual storage media inside the storage itself, and then learn about the various means of access and connection into these arrays. We'll then start talking about how the storage is actually presented to your SQL servers to use. We'll end the module by talking about certain storage features that you may or may not be aware of that you can leverage to improve certain aspects of your SQL Server environment. First, let me tell you about one of the biggest challenges I see frustrating DBAs all over the place. Have you ever had an experience where you get long I/O alerts inside SQL Server's error log during a period of time when you know your storage is really struggling to perform well? A long I/O alert is a situation where it takes over 15 seconds to complete a single I/O operation, and it stores all occurrences of these to your SQL Server error log. When you call the storage administrator and ask them to investigate, they say everything's perfectly fine, that their storage is performing admirably, and that your numbers lie. In essence, they're telling you to get lost, because their telemetry says you're barking up the wrong tree. This results in everybody being upset and starting to blame the other team for bad telemetry. In reality, both sets of numbers can be completely accurate. There are at least 6 different components in the platform between your SQL Server long I/O alert and their storage medium. The scenario is one that I see over and over again. We're going to walk through why both layers are accurate and discuss all the pieces in between so that you have a better understanding of how to address this if and when you see this. Let's start by defining the characteristics that I look at when discussing storage performance. The first, and arguably the most important, is latency. This is the speed at which a read or write from disk occurs. When it comes to SQL Server, faster is always better. The slower storage out there responds in milliseconds, and the faster storage now responds in microseconds. The next is I/O operations per second, or IOPS. This is the measurement of the demand on the storage. If the demand from your SQL Server workload is high, then you're requesting lots of data. Your IOPS rate increases, and hopefully your storage can meet the demand. Some storage vendors broadcast that they can deliver obscene numbers of IOPS. While higher is always better, if the demand is low, being able to handle a very high amount of IOPS is irrelevant. What I truly care about here is that the storage can deliver performance, usually in terms of latency and then IOPS, at or exceeding the rate of demand from the database servers. If I'm demanding 3,000 IOPS and your storage vendor claims to be able to deliver 1,000,000 IOPS, does the million claim really matter? The next is throughput, usually seen as megabytes per second. All throughput actually is just IOPS multiplied by the block size of the I/O request. Usually, throughput is the easiest way to determine if we have an interconnect bottleneck, as certain types of interconnects can only transmit at a fixed peak speed. For example, 10 gigabit networking can usually perform between 900 and 1100 megabytes per second. Anything above that is impossible on a single 10 gig connection because of the throughput limits of the interconnect topology. Many different types of storage mediums exist out there. If you start at the bottom of performance, you end up with spindle-based storage. Fast forward a little bit, and you get SATA-connected solid-state disks, and then for the enterprise, SAS-connected solid-state disks. A more modern platform will give us non-volatile memory express, or NVMe, and then the fastest possible thing that not many people have heard of today is persistent memory, or PMEM. We'll start diving into the details on the spindle-based disk. Think of it as a multi-layer record player, if you're seasoned enough to have seen one of those. We have a magnetic disk called a platter and a reciprocating arm that can read the data as it passes by as the spindle spins. These have been used for over 50 years to store data and are great at being currently capable of very high capacities and being relatively inexpensive in the market. However, when you ask for a byte of data from disk, it has to figure out where on each spindle the data is at, move the arm to where the data is located at, and then read it as it passes by as the platter spins. This results in very high latency, up to 5 to 20 milliseconds per command, and low throughput to each disk of maybe a couple hundred megabytes per second. Because this also contains many moving parts, these are less reliable than some of the more modern storage medias. Spindle disks are still heavily in use in the data center because of their inexpensive price and their high capacity. I'm not completely opposed to spindle disks myself if I need archival data, because this could be an appropriate solution that maintains our budget. However, because of the lower reliability of these disks, I've been leaning more heavily towards a more modern solution. Solid-state disks are essentially persistent flash memory. They have no moving parts. It's basically blocks of very high-speed read and write flash memory cells with a controller that understands where your data is located at. Because we don't have spinning disks or moving parts, these draw far less power and have much higher performance characteristics, especially low latency for random disk access times when compared to spinning disks. Read and write latencies are usually less than a millisecond each. They're also much more reliable nowadays than spindle disks. Now, when I talk the interface to these disks, specifically the SATA interface here, I'm talking about the connections from the back of the disk to whatever device is being connected to. The SATA protocol has a limited number of concurrent I/O commands associated with it and usually has a maximum throughput of approximately 600 megabytes per second. When compared to spindle disks, they have a lower capacity and a higher cost, but are much faster. Now take these solid-state disks and connect them to a more enterprise-grade connection interface, in this case called SAS, or Serial Attached SCSI. SCSI is a legacy interface for older servers, but it isn't really used anymore. Modern SAS connections are similar to SATA connections, but with a higher number of inbound I/O concurrent commands. They still have all the same performance and availability characteristics of SATA disks. Now, the bottleneck to performance on SATA or SAS flash disks were always the controllers and not the actual flash cells. The primary performance bottleneck was that the inbound I/O handling had a limited number of queues, as the architecture was inherited from spinning disks. A little while back, a number of really smart people decided to reinvent the storage connection mechanism. They decided to use a faster interconnect component called PCI Express to create a new server storage standard called Non-Volatile Memory Express, or NVMe. These even have faster performance characteristics, as they can handle lots of random concurrent operations much better than their predecessors and have much better throughput rates. PCIe version 3 has a maximum throughput rate of up to 3.2 gigabytes per second, and in the latest format, PCIe version 4 has maximum throughput rates at over 6 gigabytes per second. Whereas the other disks' latencies are usually measured in milliseconds, these disks are measured in microseconds. Usually, we'll see 100 to 400 microseconds per read or write operations with these types of drives. These storage devices also have a much higher queue depth, over 65,000 on each of over 65,000 I/O queues. They're also much smaller, so we can pack more of these into a given enclosure if needed. These drives are more expensive and are in a new format. Your enterprise servers might not have caught up with adopting these disks because the connection mechanism may not be present in older servers or storage. Persistent memory, or PMEM, is an up-and-coming storage technology that is absolutely amazing, and you should know more about it. Think of it as regular DRAM memory with NVMe cells on it and a supercapacitor. Whereas regular DRAM loses its contents as soon as the power is cut, PMEM can hold on to this information long enough to write it to the NVMe storage on the device. Therefore, PMEM allows us to think of it as storage that is so fast its access time is measured in nanoseconds, but ensure that it's persistent in the event of a power loss. The last thing we want is database corruption underneath any of our servers, and PMEM becomes a phenomenal answer. As of the beginning of 2021, it's very new on the market and is being developed by Intel. It requires special memory and a physical server that can handle this. Right now, you can use this with virtualized SQL servers, but you have to realize that this becomes immovable between hosts, as we don't really have PMEM available in a shared storage configuration yet. I ran across one customer that was exploring PMEM, and they tested this on a server that was doing some substantial nightly ETL. Their nightly SSIS packages were averaging about 3 hours and 45 minutes to complete. They put the databases on a local PMEM drive, and without any SQL Server changes, the ETL ran in just 8 minutes. That's absolutely incredible, but you don't want to know how much that server cost. I'm not going to spend much time on PMEM, as it's still up and coming and I rarely see it in the field, but if you're intrigued by what I've been saying, feel free to read up on it at the Intel website. Historically, systems engineers have focused almost exclusively on the capacity of the storage underneath your servers. What I mean by that is that when they go to purchase new storage, they look at how many terabytes or petabytes they use and make a purchase based on the stored data and estimations from how much is being added each month and year. These high-capacity spindle drives are great for high-capacity systems, and the appropriate disk pool design will yield good reliability, but these are generally quite slow and not good for widely shared environments. These platforms are very good for archival and historical data, especially data that changes infrequently or not at all, and are almost always less expensive than their flash components. Sometimes these systems can even contain data savings options such as inline deduplication and compression. However, more modern systems and the demands on them have started to focus more on the performance side of storage. While these systems might have lower available capacity, they're generally more reliable because they don't have moving spinning disks. The low latency nature of the storage media means that we have a very low latency to the storage inside and much better random storage access patterns. This lends quite well to virtual environments due to the distributed and scale-out workload demands of the virtual platforms. They are more pricey though, but the prices have come down considerably in the last few years as the prices of the underlying storage media have decreased. Now that we've discussed the kinds of storage, let's talk about the enterprise storage classes that you'll encounter in your data centers. The least costly option is direct attached storage. Lots of people argue against direct attached storage, but I claim that it has its place. More on that in a minute. The next is network attached storage, or NAS. The next is a storage area network, or SAN. The next, and you may not have heard much about this, is hyper-converged or software-defined. Finally, there's cloud storage. Let's look through each of these to understand their characteristics and use cases. We'll start with direct attached storage, or DAS. DAS can comprise of any local storage to a single physical machine. It could be inside the server or connected via an external chassis. It can be made up of spindles, SSDs, or NVMe disks, or all the above. Because of the wide variety of these devices, the performance characteristics can be quite variable and all over the place. There's so many variables involved with understanding the performance of these devices. Spindles, or SSDs, that are SATA or SAS connected each have an individual throughput cap of approximately 600 megabytes per second. NVMe is one of the fastest options out there if you have the slots for them. PCIe-based storage is also an option, but you may be limited by expansion slots. If you're looking for the fastest possible storage at the lowest possible price, this is where you should start. You do have that whole challenge of a single point of failure in the physical server, but SQL Server high availability features can help you minimize the risk and maximize performance while keeping the cost down. But the overwhelming majority of the systems I see in modern data centers use shared storage devices simply because of the time spent to manage these individual storage devices and the fact that these are single points of failure. I'm going to focus my efforts there. These shared storage devices are much more complex than storage present inside a physical server. Not only do they contain the storage media itself, they also contain the brains to understand where the data is located at that you're asking for and must be redundant in nature to facilitate outages and failures. The storage controllers inside of shared storage devices are arguably the most important pieces of the devices. They handle the metadata for the location of the data that you're requesting, sort out the data so that it can write it when you make changes to the data, and can contain read and write caches to both streamline disk access and make them perform better. Some of them even contain features such as inline compression or deduplication to reduce the amount of data written to disk and make those operations more efficient. Next is the storage media itself, and can contain any number of drives and types of drives. These can be coordinated into a set of disks called a disk pool that provide both performance and fault tolerance if a disk were to fail. Finally, since this is a shared storage device, these devices can contain either network or fiber channel adapters so that external servers can connect to these devices. You normally have at least 2 ports per controller for redundancy in case an interconnect port or a cable were to fail. This added complexity is pretty necessary since it sounds like we're putting all of our eggs in one basket with these shared storage devices. These have to be much more resilient to faults and failures so that they don't go down and crash every server connected. Thankfully, these are much more reliable than traditional attached storage, but they do come with varying degrees of price tags. The lowest cost and usually the lowest performing type of storage is the network attached storage, or NAS. A NAS comprises of a low-powered controller and any type of disk that either the vendor or you decide to put in it. The device on the screen is by a manufacturing vendor called Synology and is a good example of a reliable NAS. I own 4 different units myself. You can pile storage into these devices and provision a large disk pool free to use by any number of servers at a very reasonable cost. These perform admirably well for centralized things like SQL Server backups or other secondary storage tasks. They're quite flexible and have a lot of bells and whistles associated with them, but may not be fast enough to handle medium to large database workloads. You can see on the screen, this is my primary Synology network attached storage device. I absolutely love this thing, and this is not trying to be a marketing or sales pitch. There's a lot of other really good arrays in this category. This is a relatively inexpensive 12-bay rack mount unit, but they go all the way down to 2-bay standalone, all the way up to 24-bay. They're awesome. They're super flexible. If you notice, I've got 2 disk pools in this device. Storage pool 1 has a total capacity of 54.5 terabytes. Storage 2 has a capacity of 13.6 terabytes. I have my virtual machine workloads scattered between the two of these. Disk pool 2 here, they're a little bit older disks, and I've got some solid state cache enabled for that disk pool. I use this as network attached shared storage to my VMware and my Hyper-V environment. It's got iSCSI, it's got NFS, and it's got SMB3, so it's super flexible. It works really well with pretty much anything you want to throw at it. I also use this as a backup to disk target for my SQL Server backups. It's phenomenal for that use case, and this thing can actually replicate out to the cloud. It can replicate to other Synologies. It's really flexible, and just gives you a lot of really good benefits. Now, if we open the resource monitor here, a lot of good telemetry out of here. We can see CPU utilization statistics on the controller, memory amounts, network throughput, iSCSI throughput, disk utilization percentages, all kinds of really good information. The thing that I liked is the IOPS meter on the individual disk pools. Nice and healthy, happy. It's just a good, solid, albeit not as fast as an all-flash array, but it does its job quite well. This particular array has got 10 gig network adapters built into it. You can add more if you needed to, and it just, quite frankly, works. Next up is a storage area network, or SAN. A SAN is usually considered higher end in terms of overall capacity and performance characteristics. These usually have multiple sets of everythings, including controllers, interconnect ports, power supplies, and drive backplanes. These are tough devices that are historically built for absolute reliability. Recently, and I would say within the last 10 years, I've seen a very concerted effort on behalf of the SAN vendors to start to improve the performance of these devices. Not all SANs are created equal. The price tags are quite varying because of their performance characteristics, available space, or features. If you look at the lowest performers to the fastest performers, spindle SANs are just that, shared arrays containing a small number of spindle disks that are shared to multiple servers. Tiered and hybrid introduce solid-state drives to boost performance. All-flash and NVMe-based SANs take performance to the pinnacle of speed. A spindle SAN is getting harder to come by these days. These usually have higher storage capacity, but rather low performance characteristics. They usually have low to medium peak possible throughput rates, meaning between 100 and 400 megabytes per second, and the highest read or write latencies of this type of storage. They're quite inexpensive compared to the other tiers, and they're certainly reliable. I just feel that if your budget can allow for it, you should look at introducing some flash into your storage because of the elevated read and write latencies associated with spindles. Tiered SANs came about when storage vendors decided to replace some of their spindles with a few small capacity SSDs to boost performance. They took a smart approach. Add them into a disk pool, make them available for the end users to place selected objects on to get better performance. Some of them are even smart enough to detect quite active blocks on disks. It keeps track of what's active and what has changed, and if this block is quite hot during the day, it'll move that block automatically each night onto a faster tier of storage available. It was a great way to boost performance transparently without having to micromanage where each object is placed. However, what if you're accessing critical data on the beginning of each month for end-of-month reporting? I need all this data right now, but it's on a slow tier of storage. The SAN marks that it needs to move to the faster storage tier tonight, and it does, but at that point it's too late. I don't need the data to be fast tomorrow. I need it right now. Other types of tiered SANs will leverage SSDs as read and write cache to boost performance. However, a more modern architecture was introduced relatively recently called hybrid storage. A hybrid SAN uses lots of flash and maybe some spindles, maybe not, in conjunction with a lot of RAM to move this data in real time based on your access patterns to maintain performance for the hot data and place on the less expensive storage the data that is accessed far less frequently. It has better performance characteristics than a traditional SAN and usually results in average latencies to disk being much lower than a spindle or tiered SAN. These can be more expensive than the other two, but you get what you pay for, and this usually results in pretty good balance between performance and price. An all-flash SAN has no spindle disks whatsoever. These are extremely fast. Usually these contain overbuilt CPU and memory architectures on each storage controller and have SATA or SAS connected SSDs in their storage pools. These perform incredibly well, usually at or below 1 millisecond in response time. Believe it or not, in this class of array, the performance of the controllers is the largest impediment to performance. They have a high amount of read and write cache on board and the metadata management to understand where your data is either being read from or written to is the bottleneck to performance in most cases. These are one of the more expensive storage options, but prices have been dropping over the last few years to what I would consider reasonable levels. Depending on your organization's approach to keep replacing storage, because there's no moving parts in these arrays, you can usually keep them longer and financially amortize them on a different schedule than spindle-based arrays. They might actually work to be equal or less money over the lifespan of the array. The last class is a SAN with NVMe storage. This is your fastest possible option. I list here that these have lower capacities than the others, but it's because the price per terabyte is higher. You can configure them to quite large amounts if your budget allows. These have the best response time under heavy demand or high concurrent access patterns. As with all flash SANs, the controllers continue to be the bottleneck to performance. That said, these usually perform so well that we're still talking far less than 1 millisecond access time under all situations. This is a flash hybrid array from Western Digital. It's their IntelliFlash lineup that they recently sold off to a company called DNN by Tintry. This is a flash hybrid array. It has a combination of a good amount of memory per controller, a decent amount of SSDs, it's enough to facilitate, and a number of 15K SAS disks. This is live in production right now. You'll notice that we have two hybrid pools, meaning we've got two shelves of disks connected to the controllers. We've got data reduction at 1.5x. You can see we've got two LUNs provisioned on here, and our average latency over the last 5 minutes, 0.5 milliseconds, 0.3 milliseconds. It's not really doing too much right now. It's just kind of hanging out because most of these are application servers. They do have a couple of database servers on here, but they're pretty quiet right now. And you can see that on average, our latency is really good, 0.3 milliseconds. You can see that when it has to drop down to spindle media, it's bumped up to, 2, 5, 9, maybe a little bit higher, just in short periods. But for the most part, this thing does really, really well. And we can take a look at the other disk pool here, and you'll see similar results. In fact, this one looks a little bit better, about 3, 2.5, 3 milliseconds. No big deal. This thing is just sitting here humming along. Our CPU utilization, 2-3%, over 99% cache hit ratio, meaning either memory or NVMe disks for a really fast acceleration. And honestly, this thing just works. Most of the time, everything that we need is either in DRAM on the array or it's on the SSD tier. For stuff that's just sort of hanging out, it'll drop it back down to the slower tier when needed. But if it needs it right now, it'll go grab it, move it back onto the faster tier, maybe move something back in its place. But honestly, it's another one of those arrays that just works great. It's perfect for their needs. It's a low impact, relatively inexpensive array that performs quite well. Okay, let's take a good look at a really solid lower end all flash array. Now lower end, I mean they sell a lot bigger ones than this. This particular array is a little bit older array from a company called Pure Storage. It is the M20 array. They actually sell the NVMe version of this now. I've got a moderate workload running in the background here, and you can see their dashboard here, capacity, latency, bandwidth. So you can see in terms of IOPS, it's writing 2,000 IOPS roughly, bandwidth 90 megabyte a second writes. You can see our latency numbers though. This is where all flash truly shine. Reads 0.14 milliseconds. Writes 0.28, 0.3, that is phenomenal. That is exactly what I want to see. And this level of telemetry is available to any administrator of an array like this. The fun part here, this is at the array and the disk pool. I can also go into the performance characteristics and I can look at the overall array. I can look at individual volumes. So I can see the LUNs, they call it the volume, and I can see what's actually going on here. All this telemetry is available for you to go mine, and this is why it's so important to work with your storage administrators and everybody else in the environment. Because having this level of access, if you think that there's a storage problem going on, and you've got something going funny inside SQL Server, and you look here, and everything's perfectly fine, they're not lying to you when they tell you this. The problem exists above this layer. So now you've got really good telemetry, and you can see this is honestly one of the best performing arrays on the planet. It is phenomenal. is exactly what I want to see. Anything over about a millisecond on this particular array is just too much. The next storage architecture that I want to spend a good amount of time on is hyper-converged or software-defined storage. This is a relatively recent development in the storage landscape, and I would consider it non-traditional. Think of it this way. Get rid of a regular separate SAN. Pack your virtualization server hosts with a lot of attached storage. It could be all flash, or it could be a combination of flash and spindle media. Place fancy software on each host that allows each one of these storage pools to be shared as a group and managed for redundancy and performance. Use this software to bind it all together and present it to each physical server as if it were a shared SAN. Let me illustrate this for you. In this diagram, you see 3 physical machine hosts, each with a lot of CPU, memory, and storage. Each are connected to each other with very high-speed networking. The red VMA that you see on the diagram is a virtual management appliance, which is a virtual machine located on each physical server. This virtual machine understands how to replicate any data that is changed to at least one other host in the host cluster for redundancy and knows where the data is at that you are asking for. These VMAs and direct attached storage are coordinated to become a network attached storage device. The VM layer in each physical machine is not aware that this is distributed storage. The storage layer handles replication and availability and maintaining performance between the various physical machines. While this architecture is arguably cutting edge and very easy to manage in theory, from a SQL Server perspective, I have a very tough time recommending this sort of architecture. The performance characteristics of these storage types are usually slower than all-flash SAN equivalents. Database engines are known for their larger block size read and write patterns with a high amount of random I/O, and these types of storage devices do not perform as well with a larger than normal block size. For example, SQL Server can read data in either an 8 kilobyte, 64K, 256K, or 1 meg and beyond block size. SQL Server even writes data in a 60K block for logs. Hyper-converged storage usually has a significant performance penalty when compared to an all-flash SAN for these type of operations. You don't have to believe me. Test it for yourself and confirm the differences. Also, when compared to an all-flash SAN, and even if the storage in all of these servers is all-flash, the management appliance present on each physical machine is going to consume a high amount of CPU and memory on that host. The marketing literature for each of these claims no more than 10% per host. However, in my experience, it can be between 5% and 40% of the available host CPU cores and memory. This CPU and memory overhead is on the same physical CPUs and memory that your virtual machines need to operate. This special storage layer will always come first in the hypervisor scheduling queues, so if your storage activity ramps up, your SQL Server workloads could suffer a performance penalty as a result. Also, if you are doing host-based core licensing, you now have a high amount of physical CPU cores that you have paid a lot of money to license but are functionally unable to be used for your SQL Server workloads. You cannot isolate these CPUs and remove them from your SQL Server licensing footprint. If you have a 24-core physical server and that you were doing enterprise-based SQL Server licensing for, you could have up to 40% of your CPU cores fully licensed but never able to be used for SQL Server workloads. Think about how much money that adds up to if you have 4 or 8 or 16 of these hyper-converged servers for your SQL Server farm. That amount of money could buy you a traditional all-flash SAN that would probably perform better. Cloud storage is somewhat easier. When compared to their on-prem equivalent, storage in the cloud are things you simply provision, attach, and use. It could be a managed disk, and you get to pick the performance characteristics of what you provision. It could be a standard hard drive, which is a spindle disk underneath. It could be a standard SSD, which is most likely a regular SATA or SAS SSD. It could also be what they call an Ultra or Managed IOPS SSD, which is most likely an NVMe disk. Because of the scale of current economics, all of these are probably local disks. They are sure to have synchronous replication so that they have redundancy in their data centers. It could also be blob storage external to your virtual machine, and we have no idea the performance characteristics or underlying media of that. It's usually fast enough for our purposes, but you're free to test these as needed. We just provision the disk type, size, and then either connect it to the virtual machine or write things directly to the storage platform. It handles everything else for you automatically, but everything that we've talked about is still present underneath what you have visible. Storage from any of these devices can be connected to your virtual machine host for you to provision virtual disks with a number of different ways. The most common is block level presentation. What a storage administrator does is create a logical chunk of storage on the SAN and presents it as what looks like a locally attached disk for you to place your database virtual disks onto. It could be connected through fiber or software through iSCSI. It could also be configured as a network share type connected storage, connected through either NFS or SMB3. Special permissions are needed so that you and only you see the storage that are presented to a given virtual machine. Usually these are managed well so that the storage is only connected to the physical servers that it needs to be connected to. If you're talking block level, either through fiber or software such as iSCSI, it looks like locally attached hard drives to that physical server or set of servers. A LUN is created on the SAN and presented to each host in the virtualization cluster. That LUN is then formatted for the VMware Clustered Shared File System, in this case VMFS, and called a data store. Every host in this cluster can read and write data to this data store. These data stores are then used as the place where your virtual disks for your VMs are located on. There's redundancy at every level so that if a network switch port fails or a SAN controller is reassigned, no one notices the difference and things keep working. Network presentation is very similar to block level from our perspectives. A share is created on the SAN, which is then mounted as a data store directly. It's not formatted in any specific format to VMware. Our virtual disks for our SQL servers can then be placed onto this data store and used just like the other. The space allocated on these data stores are not always what they seem. Space reclamation is absolutely vital for your storage administrator, as many business units have gotten into the habit over the years of asking for much more storage than they actually need. What a lot of storage units now allow them to do is to present storage for you to use, but have not actually allocated all of it, just in case you don't actually need it all. This is called thin provisioning. Thick provisioning is just the opposite. It's when they allocate and reserve everything that you asked for. Now, before you start saying I want everything thick provisioned, thin provision is fine in some cases as long as it's managed properly and expectations have been set. Let's take this scenario where my SQL Server has 2.1 terabytes of virtual disks on a 4 terabyte VMware data store and corresponding 12 terabyte SAN disk pool. If the LUN has been thick provisioned, that 4 terabyte LUN has blocked all 4 terabytes from being used on the SAN. 8 terabytes is now available on the disk pool. However, if that LUN has been thin provisioned on the SAN, then only the actual space consumed by my SQL Server virtual disks is what's consumed on the SAN itself. On the same 12 terabyte disk pool, 9.9 terabytes is actually available. There is a high likelihood that any of your SANs for SQL servers are provisioned in this manner. Don't be alarmed, as they should be managing this properly. The challenging part gets into if space is consumed at a very quick rate and they're not watching, you can run out of space on the disk pool because they're probably overcommitting that storage and allocating more than actually exists. It's rare to see this, but it can happen. Your storage is not entirely dull. Some storage arrays have some advanced features that we can leverage to both boost performance and add features that can both save us money and give us some interesting little tricks. The first is with inline data savings. Since the metadata inside the SAN controller is what determines where and how your data is being stored, we can do a few tricks to make this better. The first is to compress the data inline. You know that a lot of your SQL Server data is text-based and can probably be compressed to save space. If you've ever explored SQL Server table-level compression, you know exactly what I'm talking about. The SAN should have extra CPU to spare. They can leverage available processors on the controller to perform inline compression as you write data to save you space on the SAN. While normal databases can be compressed by a decent amount, SQL Server table-level compression is more like a deduplication algorithm and is built for performance, but not necessarily maximum compression. Depending on the type of storage array that you have, you may be able to get much better compression rates if you perform this level of compression on the storage itself rather than in the database. The next is deduplication. These arrays can be smart enough to know that you were going to write the same block or not. Why write it twice? Why not just write a pointer to the first block and both save space and make the operation faster? Think of the savings on disk if you have a production database that is backed up and restored for pre-production development uses. Deduplication can save you many terabytes worth of space. The metadata handling itself can also become strategic for use for certain operations. Give the data that has changed in the last hour is tracked and that you want to revert to an hour ago because an upgrade failed. These arrays are so smart that you can actually wipe the changes and very quickly revert the state of the data backwards in time. Other situations can make life even better. One of my favorite tricks is to take a SAN LUN and clone it. Present the cloned LUN as a new one to a virtual environment. It's just metadata, and it takes mere seconds. It sounds kind of fishy, but what if you cloned a SAN LUN that contained a 50 terabyte production database? What if you then presented this cloned LUN as a new LUN to your VM environment and then connected the virtual disk on that LUN to a pre-production virtual machine? The production database that is now on the clone can then be presented to the pre-production SQL Server and effectively speed up the process of what you would normally do to do a database backup and restore. A database backup could take hours of a database that large, and the restore could take equally as long or longer. If you did this on the SAN itself, it is simply metadata inside the controllers. I've personally done this with a 70 terabyte database, and the refresh process to go from production to pre-production took 42 seconds. Think about how that might be strategic enough for you. The biggest challenge with all of these is that your SAN must contain processors fast enough and advanced enough to allow you to do all of these things. Some SAN vendors claim to be able to do a lot of this, but their controllers are not robust enough to be able to accommodate these features without imposing a significant performance penalty. When it comes to SQL servers, that is the last thing that you want. Explore how fast your controllers are to make sure that you can turn on some or all of these features without any measurable performance penalty. Now let's just say that your storage has controllers and features capable enough to be able to enable some of these data savings features. Take that previous example where we had 2.1 terabytes of SQL Server objects and a SAN LUN of 4 terabytes. Let's assume that our data was somewhat compressible and we were able to get a 3-to-1 data savings ratio of the data on the SAN LUN. We have 2.1 terabytes worth of data itself, and at that savings ratio, that means we've only written 700 gigs to that actual disk pool on the SAN. That freed up even more space on the SAN to be used for other purposes. The only caveat is that the SAN controller processors must be fast enough to accommodate this load. Some are, some aren't, but advertise the features anyway. You can tell if the SAN admin enables data savings on the SAN if your storage latency on your SQL servers immediately rises. Now you can see a production all-flash storage array that has inline data savings enabled. This has one solid-state disk pool. You can see it is performing incredibly well. We've got top LUNs, latency, IOPS, throughput. The data savings thing here is what I'm really curious about. You'll notice original data, 63.9 terabytes, compressed to 26.7 terabytes, so 58% compression rate. Deduped to 22, so an additional almost 7.5% saved. That is a 41 terabyte savings. So literally 2.9 times data reduction from the original data. That's awesome because that means we can actually buy less storage than we actually need. Let this thing do its magic. There are a lot of SQL servers on here. There's also a lot of file servers and app servers. For your SQL Server workloads, on average, I would expect to see about a 2.2 to 2.5% data reduction if it's just SQL Server data on the array. If you do a lot of refreshes between production and pre-production, I'd probably expect to see more. Now we go back to my lab array here, and you can see I have a lot of different copies of basically the same database spread across probably about 40 virtual machines. You'll notice here, our data reduction ratios are a lot better than what we got on the other array, and that's because it's literally the same copy of just about everything. I'm seeing about a 4.6 to 1 data reduction on here. Now, if you look at provisioned space that's not actually being consumed by the virtual machines, we've got about a 17 to 1 total reduction, which that's just fake numbers. Really, what I care about is my data reduction, 4.6 to 1 ratio here. From a data savings standpoint, that's really good. So if you've got workloads where you have lots of copies of the same bits of data scattered all over the place, you might find that a data reducing array can save you even more. As I've mentioned before, nothing is perfect. Certain SQL Server object types or actions can cause some challenges with inline data savings on your storage. The first is with database level encryption. If a database is using TDE or has lots of encrypted data inside the database itself, that compressibility of that data is dramatically reduced. Databases with lots of encrypted data will show much lower data savings ratios on the underlying storage. If your databases apply encryption in any way, make sure your storage administrators know so they can expect lower data savings rates as part of their storage projections. Lots of blob data, such as documents or images, stored in a database result in much more overhead and challenges with storage level compression. The data is rarely compressible, and if the storage has no ability to turn off compression, this could lead to both storage performance penalties and elevated CPU consumption on the storage controller itself. Usually, we have plenty of controller CPU to spare, but if it's creating a performance penalty, that's usually not very tolerable. The next is with column store indexing. Column store is absolutely amazing when it's used for the right purposes, but it is incredibly compressed on disk. Your storage will most likely not find any additional compression opportunities underneath column store indexes. This isn't always a bad thing, as column store is incredibly strategic to use in the right use cases, but just keep in mind that your storage data savings may be reduced if you use column store. The last scenario is underneath SQL servers that are very demanding. Given the nature that many of these operations are performed in line, if your storage consumption rates are very high inside your SQL servers, the act of trying to use some of these features at the storage layer may be enough to impose a moderate to severe performance penalty. You'll see this in the latency of the storage command starting to increase as the demand goes up. In upcoming modules, we'll talk about all the key metrics needed to detect and understand if the storage layer itself is actually causing this performance penalty. A lot of people ask me if there are ways to simulate storage level activity to determine the performance characteristics that they should expect from enterprise storage underneath their SQL servers. The only true way is to have your SQL server itself perform a wide variety of its operations under a replay scenario, such as using SQL Server Distributed Replay. However, that's a real chore to set up and probably not repeatable for storage and server admins. We can use storage benchmarking utilities, such as Microsoft Disk Speed, to simulate certain workload patterns. Do not think that these are specific to SQL Server, as the SQL Server workload parameters are quite variable and are all over the place in nature. We can, though, pick certain workload properties and run individual tests to see how the storage performs. Let's take a look at disk speed and see how we can simulate certain storage workload patterns to get a good idea of how your storage can perform. Okay, on the screen here you see disk speed. It's out at github.com/Microsoft/diskspeed. It is completely open source. You have full access to everything. It is absolutely awesome. This is the spiritual replacement for the old SQL I/O utility. I love disk speed better because it gives a sub-millisecond granularity, which for all flash and NVMe storage is exactly what you need. The source code is here. Feel free to compile it if you really want to, but you don't need to. If you go down to releases, there's a link here to a compiled version for Windows. It's both for 32 and 64-bit. I really hope you're not running 32-bit at this point. Go ahead and download this. Stage it to a folder on the server that you want to test. It doesn't have to be on a big drive because you can specify parameters to run it anywhere. So I'm going to jump over to this other machine that has it staged. I've got it staged on C drive, disk speed. And I have a batch file here. Again, nothing too fancy, but you can see diskspeed.exe. We're going to do a 64 kilobyte block test. Minus D60 means 60 seconds. Minus SH means disable any sort of operating system level software caching. SQL Server operates this way so that we're transactionally consistent. I'm going to collect latency metrics. I'm going to do 8 operations per thread and 8 threads. We're going to do a 90% read, 10% write test. We're going to use 1 gig of entropy. Now this is an interesting piece. If you don't use this parameter, the default inside disk speed is to quite literally use an alphabet. A, B, C, D, E, F, G, blah, 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 0, 1, 2, 3, blah, 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 and then repeat inside the workload test file. This is one of those things where if you have a data reducing array, it's going to detect that. And you're basically testing the storage controller and not the underlying storage at that point because it's literally just super tiny and it doesn't matter. So a little bit of entropy is going to give us complete gibberish. Neither of these are representative of an actual SQL Server workload. Your data is not gibberish, but it has holes in it. So as a result, this gets us closer to the SQL Server workload. But again, it's not identical. We're going to do a 100 gigabyte test. We're going to place this on the F drive, diskspeed.io.dat. We're going to use a greater than symbol, and we're going to save the results to results_storage.txt. Let's go ahead and run this. And you can see I'm running this in a PowerShell prompt with administrative privileges. Now, while this is running, I'm going to jump back over to the other machine, and we're going to take a good look at our storage. If I scroll down here, You'll notice this thing is sitting literally at 1.1 to 1.2, roughly, gigabytes per second. That is a single 10 gigabit network adapter that is being completely saturated. We'll just go ahead and let this test finish. While this is running, you'll also notice that the latency on here for reads is amazing. 0.12 millisecond latency, and the writes are 0.33 milliseconds. That is phenomenal. But that's also exactly what I expect to see. Okay, the test results just fell off. Let's go back to our disk speed VM. You can see it is complete. We have our results in this output file right here. So you can see we have our command line parameters here, but then it translates them into plain geek speak. Duration, 60 seconds. Cooldown time, randomization, path, think time, burst time, software caching disabled, hardware write cache disabled. This is what we want. Write buffer test, performing a mix test of read and write, 90-10. 64K block size, sequential I/O, 8 outstanding operations per thread, 8 threads, etc. It gives us an interesting readout here of the actual CPU consumption. You'll notice that our average CPU consumption was anywhere from 16 to 25%. Our kernel time is where in Windows you can actually see this amount of activity really starting to ramp up. The kernel layer is what handles a lot of I/O activity, and you'll notice that is what's really elevated there. We can then go to our individual threads on the 8 cores here, and we can take a look at the IOs, the bytes read and written, megabytes per second. You can see it's fairly evenly distributed here. IOs per second, average latency, standard deviation. If we go down, read and write, it breaks it out. So, about 22,000 IOPS for reads, 2,400 for writes. Average latency, 2.3 milliseconds. You notice that is not what we saw on the storage array. Very, very interesting. As we go through the performance side of every layer above this, I'm going to show you why this metric here does not line up with what the storage array showed us. The other fun part here is this gives us a latency read and write percentile spread across the entire test. You'll notice that if you hit the 99th percentile, it's higher than the 95th, 90th, things like that. But then we hit this point of inflection right around 3.9s or 99.9 percentile. At that point, it starts to spike up. This is the fun part. We can start to tell that if the latency spikes that we were experiencing were statistically significant or not. I claim that most of the time we just care up to about here. Those are still high. That's because the defaults inside the virtual machine layer, the hypervisor itself, were all set to default, and these kind of storage queue stack-ups are very common. I'm going to show you as we go through the remaining modules how to detect this and how to fix it. All right, that about covers enterprise storage from a conceptual level. We're going to talk a lot more about how it relates to performance tuning in upcoming modules. Next, in Module 3, let's take a look at how your storage and servers can communicate through your networking and interconnect topology.